Yes.
Okay, excellent.
You can find me a stairwell to sit in.
Okay, good afternoon, everyone. I'm pleased to introduce today's speaker, Dr. Michael Hart. He's a professor from College of Optical Sciences, University of Arizona. And before that, he was a research faculty at the Department of Astronomy. I also want to mention that he is the founder and president of Hart Scientific Consultant International, and a very successful startup. So it's a perfect example of being a faculty, also an entrepreneur at the same time. If you want to know more about him, he also likes riding horses in his spare time, and along with recognizing complicated wavefront through turbulence. And so Dr. Hart, his flight has been canceled tonight, so he will have more time to interact with the faculty and students, perhaps sometime tomorrow, if you're interested in talking with him more. Okay, without further ado, Dr. Hart.
Yes, thank you very much. I was telling some of you earlier that I'm very embarrassed that I've spent 30 years in this field, and this is the first time I've managed to make it to RIT. But now I get to spend another 24 hours here, thanks to the weather. So I'm looking forward to taking advantage of that, instead of having to go back and teach in Tucson tomorrow morning. I did warn my class this might happen, and they're not off the hook. They have there's some reading they have to do. Let's talk a little bit about wide field computational imaging through image restoration through the atmosphere, which is one of the things my group does. I acknowledge some of my collaborators on this work here across quite a number of institutions. One never does this sort of stuff on one's own. I lead a group at the College of Optical Sciences in Arizona. This is most of us, me and my group of students, and you can tell this was taken on Halloween last year from the various funky attire, and guess who forgot to bring his Halloween costume that day? They wouldn't let me live it down, so they made me bring it.
You're dressed as faculty. That's
the next guy. Yeah, that's. I didn't stand out from the crowd, though, as you know. There's a bunch of us at Arizona that look like that. And by the way, thank you, Roger. Do feel free to interrupt, ask questions, instead of listening to me droning on for the next 59.5 minutes. Just a very quick summary of some of the main ongoing projects that I have in my lab at the moment, and then we'll focus on one of them having to do with computational image reconstruction. One that I was just talking with John Kerekes about, acoustic imaging of satellites. And you sort of go, huh? There's no sound in space. How do you do acoustic imaging? It's like laser vibrometry, but we do it with passive light. So we do this in cross polarizations, looking up at the geosynchronous satellites 36 million meters away from the ground to understand how they're about on board. Resolved visible light, this is insanity. Resolved visible light images of geospacecraft from the ground. The insanity is the 100-meter aperture that you require. If you just sort of calculate lambda over d, that's what you need to be able to make decently resolved images of even school bus-sized spacecraft in orbit. That's a work that we're doing with Lockheed Martin Space Systems Company and IARPA. Then this is the one that I love. This is one that's got all my students excited right now. I don't know if anybody here is working on Starshot, but this is the crazy idea of sending an iPhone to Proxima Centauri b, which is a quote-unquote Earth-like planet that was discovered a year or so ago, orbiting the nearest star to us that isn't the sun, about a little over 4 light years away. So the idea is to to hook up a small chip to a 4-meter solar sail, then blast said poor inoffensive solar sail with 100 gigawatts of 1064 nanometer YAG laser light launched from the ground, blast this thing to 20% of the speed of light, and 20 years later it takes pictures of the Earth-like planet Proxima Centauri and sends them back. So this is fun because I get to tell my students and myself, no idea is too crazy, you will not get laughed at, anything you think of, bring it up. It's just the greatest sandbox to play in. Then other things, we're looking at ceramic materials. I've been having great fun talking with Professor Chow about how we might collaborate on laser polishing of ceramic materials for optical systems. We're building high-stroke deformable mirrors. We're working with AFRL on how to observe satellites during the day when you have this monster background signal and all of the photon noise that implies. And then finally, image restoration after detection, work we're also doing with actually the Directed Energy Directorate of AFRL at Kirtland Air Force Base in New Mexico, in Albuquerque. So we'll be talking mostly about that today. So this is the enemy, the atmosphere through which we must look if we are trying to image far away. So on the right here is a movie, well, I guess it just stopped moving, but from a video recorded from an airborne surveillance system of the back of a ship in the Gulf of Mexico. The range is on here, there we go, 9.3 nautical miles, and there's an altitude on here somewhere, I'm not sure where that is, somewhere on here. But anyway, here's a zoom in of a piece of the back of the ship right around there, where you can see the effects of what 9 nautical miles of relatively innocuous atmosphere does. There's nothing particularly wicked about this particular air path, but nonetheless, this is not exactly what you would call diffraction-limited imaging. Right? There are a couple of effects that we can identify and then think about how we might tackle them. The point spread function is clearly a dynamic function of the line of sight. It's not the same in optics speak. The PSF is not shift invariant. It's highly shift variant. Local blurring of the image caused by diffractive effects, and larger refractive effects that are causing this image warping. Changes in the mean wavefront tilt that vary depending on the line of sight. So if you just think about normal methods of compensating images, it's hard to imagine how you would do it in situations that look like this. So one of the goal that we've set ourselves as a team at OpSci, dreaming the impossible dream. What features would we like to have in an optical system that's designed to sharpen images? Just sort of blue sky, as it were. What would you like to have? So you would like to get diffraction-limited image quality, where your resolution is limited only by the physics of the size of the aperture and the wavelength of the light you're looking at, not by the medium through which you're looking, with high Strail ratio, so lots of energy in the diffraction-limited component of the image. We'd like that over an unlimited field of view, please. I'll take 4 pi steradians if I can get it. And without requiring cooperative beacons. So if you've ever read any of the literature at all about adaptive optics for astronomy, you'll be familiar with the idea that laser guide stars are used, of creating a beacon in the sky such that you can see the effects of the intervening atmosphere on the beacon as the light comes back at you. You essentially can look at what the beacon, you can look with a wavefront sensor, as we'll get into, at what the beacon does look like, compare that to what you know it should look like, and make appropriate corrections to your AO system. We would like to dispense with the cooperative beacon for various reasons. The military doesn't want beacons because they don't want people, the bad guys to know where you are. It's a giveaway. It also requires what they call swap, size, weight, and power. If you have to have a beacon on your system creating a laser, for instance, you need something that weighs a non-trivial amount, takes electrical power, and so on. You'd like to do away with all of that. And you'd like not to have to wait for the image. You don't want to have to collect a bunch of data and then wait 6 hours for the computer to do its processing. before you can make a decision on the basis of your imaging. You'd like it now. You know, as in real estate, you can pick some subset of those, but it's very hard to get all of them unless you do this. You suck away all the atmosphere, right, which astronomers in some sense would love to do, but frankly, it's not really practical. So we're a long way from achieving it, but that's what motivates us. Now, this is all, again, as it were, pie in the sky. You really need a concrete concept, a system that you can tie all of this technology development to in order to make it a reality. So we've chosen something that looks canonically like this. This is an eyeball in the sky. They make these at Raytheon Space and Airborne Systems in McKinney, Texas. This is an aperture here for a roughly 8-inch diameter telescope. There are various other apertures here for laser ranging optics and other kinds of sensor. So these systems are used for surveillance, search and rescue, for mapping, for a range of different airborne applications. In order to be able to fly a system like this, you want it to weigh nothing, cost nothing, take no volume, and consume no electrical power. Again, you can't have it all, right? There ain't no such thing as a free lunch. So there's a space within those 4 parameters within which you can optimize as a systems engineer. But anyway, this thing exists, clearly. There's an example. They call it the multi-spectral targeting system or something like that. And we take it as a point design. Can we build a system that does what this thing does, but does it better with lower cost, lighter weight, et cetera, et cetera? And we set ourselves some goals. We would like to build a system like this with a roughly 30 centimeter aperture and 0.15 degree field of view that is indeed corrected to the diffraction limit under the expected operating conditions of a system like this looking through, say, 10 miles of air. And if you think about what a system like that would take, there's a lot of technology development that would have to go on beyond the present state of the art. And we're tackling, in some sense, each one of these areas, and we'll be focusing on the one in the top left, the wavefront sensing. So again, this is what you would like in your wavefront sensor. This is the heart of any high-resolution imaging system. You have to make measurements of the aberration before you can do something to correct the image. And there are various things you can do to correct it. You want a sensor that is linear. That is to say, it produces a signal which is linear in the quantity you're trying to measure, in this case the aberration. High dynamic range, we need 3-dimensional characterization of the aberration because the wavefront aberration that our system is looking at is we're looking through volume turbulence, as they call it. It's essentially a 5-dimensional quantity. The optical path difference, the optical path error, in our optical system is a function of the 2 spatial coordinates in the pupil, the 2 angular coordinates within the field of view, and time. So we have this 5-dimensional quantity that we're trying to estimate. And in order to do that, we need a 3-dimensional distribution of the aberration along our line of sight, such that we can, in the computer, synthesize the effects along any chosen line of sight from the scene to our pupil. Again, no cooperative beacons. If we're going to do adaptive optics, if we're going to try to correct the wavefronts in the optics for real, then we need a deformable mirror, maybe more than one. We would like that mirror to be, unlike many that are made on the market today, we'd like it to be robust. So I'm imagining, an optical system that's hand carried and gets dropped and suffers a 20G shock when it hits the ground. Oops, I hit the wrong button twice. There we go. And I'd like it to survive. Large actuator stroke for poor conditions meaning lots and lots of microns of aberration are introduced into the wavefront. It has to have high optical quality, et cetera, various other things you would like it to have. Then there's the ubiquitous computer that, without which no optical system can be called such these days. And again, you'd like lots and lots of computing power in a lightweight architecture that consumes very little power, and an appropriate algorithm to run on it. Then the mechanical structure has requirements on it. This is one thing I mentioned earlier that we're actively working on with a colleague of mine at Arizona in the Materials Science Department, Erica Corral, and she manufactures ceramics for as the nose cones of hypersonic rockets. So they're designed to take extremely high temperatures on the order of thousands of degrees, and we realized that you can actually polish this material to reasonably good optical quality, and you can build structures out of it. So we can build an optical system out of various variations on the theme of zirconium diboride ceramic that are lightweight and robust. They're very strong, they're very tough, so they don't shatter easily. The optics and the structure, the mirrors and the structure holding them are built from the same material, so there's no CTE mismatch. Now, I complain that as astronomers, we build telescopes the same way now that we have for 400 years. Right? We take a big glass mirror, we grind on it, and we polish it, and then we put it in a structure that's made out of something else, like aluminum or steel or wood. And that's crazy. Why are we still doing this 4 centuries later when there are new materials that we can build telescopes out of? The reason is because we know how to do it. Right, well, let's figure out how to do it a different way. That's my argument. All right, so here's a piece of zirconium diboride that's been polished, and it's merely reflecting the office lights in the ceiling of my office. But I won't say any more about that project in this talk. So we've seen what effects the 10 miles of intervening air has on our image quality, but it's worth spending a moment thinking about how the various different regimes of atmospheric aberration, about what they do to our image quality. So here's a cartoon of a scenario that you might imagine where there's an airborne optical system looking down at some scene that's far away, and it's looking through atmospheric turbulence, and the turbulence is inducing aberration because the turbulence is advecting pieces of air of different temperature and therefore different refractive index. And so here's again another cartoon showing what you might expect the strength of the aberration to be as a function of altitude. Now, for those who aren't intimately familiar with the field of adaptive optics, which is probably most of you, why should you be? The strength of atmospheric aberration is measured by this quantity called Cn squared, which is it's called the atmospheric structure constant, and it is not constant, which is why there's a graph of it here, but that's what it's called in the literature. I don't know why. And it has these very peculiar units of meters to the minus 2/3, but that needn't trouble us here. Merely think of this as a measure of the strength of aberration statistically that's introduced by the atmosphere as a function of altitude. Typically, we find there's a very strong boundary layer that's caused by thermal effects of local topography and structure, buildings, trees, ground, and so on. That decays. Then there's a broad bump here up in the stratosphere, which is where you feel bumps when you're in a commercial jet, roughly 30,000 feet or so. That's where there's a shear layer of air, and that's the shear layer there that gives rise to Kelvin-Helmholtz instabilities and turbulence and aberration. And then there's another boundary layer here that's very sort of a delta function of turbulence, which is the wind blowing right over the pupil of your aperture. So it's right in your face if you're an optical system. So let's look at what each one of these regimes of turbulence does to the image. The near field turbulence, that's literally sort of in your face. It's isoplanatic. Whichever line of sight you choose, if your aberration is right here, you're looking through the same aberration. So that particular component of the aberration introduces the same error across the entire field of view. And it will basically give you an image blur that's isoplanatic, that is to say it's shift invariant. Now if you look a little further along the beam path at what happens, this is the turbulence that warps the image. So if you think about a point source down on, say somebody on the top of this building isn't terribly happy with your plane and shines a laser at you, right? And so you've got a point source of light propagating up towards the aircraft, and you've got turbulence in this mid-range here, then what that will do is essentially refract the beam of light bend it and make it look from this perspective as though it came from a different direction. It's like putting a tilted stick into a glass of water and you see the bent straw. So from the point of view of the aperture here, turbulence here makes the image move around, and because the atmosphere from along this line of sight might be different than along that line of sight, the apparent motion of those pieces of the image is different. So this is what leads to warping that we see on in the movie of the back of the ship. And then there's the stuff way down at the ground. That doesn't have any leverage to introduce warping. Sure, the aberration here bends rays, but they don't have an opportunity to look as though, there's no leverage back here for it to look as though they came from a different position. So aberration down there doesn't introduce warping, but it does introduce strongly field-dependent blurring. So this is sort of we can think of the effects here and tailor our system to address each one of those separately. So in the broad context, how do we address the problem? At a very top level, we have a scene that we want to look at. Down at the bottom, we have an imager that we're doing the looking with. And we're looking through some random medium that does its random thing and gives us a blurry image. Right. So somehow or another, we have to intervene in this rather woeful story to fix it. We need to estimate the blurred point spread function by some measurement or other and remove it. If we do that, we intervene, we compute an estimate of the point spread function, and then we remove it from the image and we get a nice sharp image. So that in essence is what we're going to try to do. A couple of general approaches. Correct before detect. This is adaptive optics. Right? You make a measurement of the aberration with a wavefront sensor, and then you use an adaptive optic system with a deformable mirror in it to correct the wavefront aberration before you make the image. This is ideal. If you can do that, you should. Why? Because it has to do with quantum mechanics. Once you collapse wave functions of the light, it stops being wave particle things and becomes photons. By the way, light is neither waves nor particles, right? It's our thinking that makes it so, right? As Shakespeare might have said. We're the ones that have it wrong. Nature always gets it right. Once we form an image, the photon noise is forever and always frozen into that image, and there is nothing you can do about it. Right? It's fundamental. So if the blur function of your aberrated wavefront has spread light from bright regions of your image into dark regions of your image, then the photon noise from that bright source will contaminate the dark region, you lose contrast. Right? And the only way to avoid that is to correct the wavefront before detection, have the photons fall where they should. Right? So that's why you should do adaptive optics if you can. The con, the why not, is because wide field correction takes, it's a huge effort. You need very bulky and expensive optical hardware, and it is done at multi-conjugate adaptive optics systems that you can read about in the literature at say, the Gemini South Telescope on Cerro Pachon in Chile. It's millions and millions of dollars worth of hardware. It takes 3 or 4 people to run it. It takes, it's an entire room bolted on the side of the telescope. Not something you could imagine flying on a UAV. Like one of the hexacopters that John was very kind enough to show me, very impressive toys that you have upstairs that I'd love to work with. But so not something you could fly on any kind of imaginable light aircraft. And if you're going to build a $150 million telescope, then maybe you spend $10 million on one of these systems. It's no big deal. But for mass production, no, that's not what you do. So the other approach is detect before correct. You make the detection of the blurred image. You just record it as it is. Let the aberration do what it will. Right? And then remove the point spread function numerically after the fact. The optics here are straightforward. They're much less expensive. They're much lighter weight. There's less of them. There's less. The mean time between failures goes up because there's less things to go wrong from a systems engineering perspective. And again, the con is that we have the photon noise frozen in. And if you're going to remove a point spread function from an optical image, it's a nonlinear process that takes a lot of computation. And the reason is because in the optical regime, we're not sensitive to phase, we're sensitive to intensity. And the intensity is the squared amplitude of the electric field vector in the focal plane, and it's the darn squaring operation that gets in the way. Right? It messes us up. Boy, oh boy, if we could only measure phase, then life would be grand and I'd be out of a job. But thanks to Gordon Moore and his law, we can now imagine building very fast computers essentially for free. Not quite literally true, but compared to the way things used to be when I were a lad, yes, you can do an awful lot with computation that you couldn't before. Nonetheless, the common theme here, both methods, either correct before detect or detect before correct, they rely on making some measurements of the wavefront aberration to begin with. So that's where it all starts. So let's say you've done that, and we'll talk about how to do that, how we do that. How do you filter out the PSF? If we have an estimate of the wavefront phases at some given field point, so you know the phases over the pupil at some point in the field, it's going to change depending on where you are in the field, it's going to change with time, then you all know this, right? The point spread function is essentially the power spectrum of the pupil function, the squared amplitude of the Fourier transform of e to the minus I plane phase. The observed image then for a given point in the field is the point spread function that we just computed convolved with the thing we are interested in. That's what we want to know. And then I always thought this would be a great name for a band, ubiquitous noise. But that's always there. Mother Nature doesn't let you make noise-free measurements. So in the Fourier domain, just take the Fourier transform of this equation. Convolution becomes a multiplication, and you can imagine doing this. Right? The Fourier transform of the thing you're interested in is equal to the Fourier transform of your measurement divided by the Fourier transform of the PSF, and you multiply by the complex conjugate of the PSF that you've estimated to make life easy, and then you have to throw in a regularizing term, gamma, to avoid noise amplification. If this PSF happens to have any zeros in its Fourier spectrum, then you end up dividing by 0, and that's always a bad idea. So then there's a whole literature on how you figure out what this regularizing factor should be. If we made gamma be literally the noise to signal ratio as a function of frequency, this would be the well-known Wiener filter. But anyway, so the thing is, the takeaway point from the slide is there is a mathematical way to get an estimate of the object we're interested in if we have a messed up image and a separate measurement of the point spread function, and you can do it computationally. This is actually really just the start. This Wiener filtering technique is just the start of what we actually do. Here's an example of what can be done. So these are two images, sort of before and after PSF removal, numerical PSF removal of the Hubble Space Telescope, observed with a ground-based telescope. So this is actually data taken with the 3.6 meter EOS telescope that the Air Force Research Lab runs on Maui. I spend an inordinate amount of my life up at that telescope. People always say, oh, you get to go to Maui? Yeah, but it's at 10,000 feet and it's in the freezing cold and I'm in rooms with no windows guarded by people with guns. So the beach, it ain't. But anyway, so they have a beautiful AO system on that telescope, and they use it to track satellites. But this is an example where we've taken a set of blurred images of the HST, and with separate measurements of the PSF using a wavefront sensor, constructed the PSF and removed it numerically. So you can see solar panels here, you can see there's the lid that opened up once over the front of the telescope OTA, the optical tube assembly, and here's an antenna. There's the back end of the telescope where all the instruments are. So that's one example where we're working with AFRL on this kind of technique. Here's another example taken from that same movie that I showed earlier of the back of the ship, where we've done essentially the same thing, reconstructed the PSF. In the HST instance, the satellite is of an angular size that the problem is essentially isoplanar. The PSF is the same across the whole Hubble Space Telescope. Here, it most definitely is not. So we had to estimate the PSF as a function of position. So to demonstrate, just to demonstrate that it's working, we sort of zoomed in on the back of the ship and looked at the name and the International Maritime Organization number, here's what you get if you just look at the raw data, and here's what you get after you clean up the PSF. And it's curious, there's the name of the port of registration, and I don't know if there are any Greek speakers in the audience, but maybe somebody can tell me why they have chosen to spell it in the ancient Greek spelling, because the modern Greeks don't spell it that way. But hey, I don't know why. But now you can read the IMO number 9103843, where I challenge you to read it here. So you know, there are various applications for numerical PSF removal if you can do it. So the system architecture that we're imagining flying on our canonical UAV looks schematically like this. We have our 30 centimeter aperture, and oh, by the way, we're going to make it a deformable mirror. So we can do some level of adaptive wavefront correction, because as I said, if you can, you should. But this is only going to correct the near field turbulence that's right up close. Now, it's an important component of the turbulence, as we saw, because it's attributable to the boundary layer whistling over the aperture of the telescope at whatever speed the aircraft's going, 200 knots maybe, potentially. Anyway, we're going to use that deformable mirror, hopefully built out of zirconium diboride, to correct the pupil plane aberration. So light comes in from the left. Light always goes from left to right. I tell my students, or they fail their prelim exams, and focus down onto a sensor or sensors, and this is the part we'll be digging into for the rest of the talk, where the wavefront sensing is done. Then there's a computation. So this is all optics, recording the real-time image, sensing the wavefront errors, and correcting the local aberration with an adaptive primary mirror. Then the information switches over from being carried by photons to being carried by electrons. And we've made some measurements with our sensors. Now we're going to do some computation here to figure out what the wavefront errors are in 3 dimensions, and then construct point spread functions. So after the wavefront reconstruction is done, we separate out the component that's close, send that to the deformable mirror, use the rest of it to construct PSFs that are now field dependent, and remove them numerically from the image, and voila, a high resolution image, we hope. That's the idea. So the key technologies here that we need to push to a significantly higher level of maturity, tomographic wavefront sensing, that is to say, wavefront sensing in 3 dimensions, through the volume of the turbulence we're looking through, and cheap, fast computation, so we can do this in real time. And if we're going to do any component of adaptive optics at all, that is to say, correcting the wavefront in real time, then it darn well does need to be in real time. You get a millisecond or less to do the computation, make the correction. If you don't, you're out of date, the atmosphere has changed, and the correction you apply has nothing to do with the aberration that's now there. You're too late. So yes, the real-time computation is important. So wavefront sensing, again, my students get tired of hearing me say this. You can't correct what you haven't measured. That's the general principle of system engineering and design that you students should take with you. The first thing we need then is a suitable wavefront sensor to tell us what the aberration is. Again, those, well, we said all of that before, what we would like our sensor to be capable of doing. And we choose, well, in my group, we have chosen to work with an imaging Shack-Hartman sensor. So each sub-aperture of the sensor sees the full field of view. Now, I don't know, maybe that everybody's familiar with what a Shack-Hartman is. Ooh, I hope the rest of that is there. So the wavefront sensor at the heart of the system, and again, I touched on this earlier. I'd love to be able to measure phase, or OPD preferably, directly. I can measure phase with an interferometer. I can't measure OPD directly, the way the radio people can. I'm always envious of radio astronomers, because they go away with their radio telescopes and they record amplitude and phase on a piece of tape, for heaven's sake, and then they go back to the warm comfort of their office and they do the correlation and the interference in the computer. I can't do that. I've got to do it in the optics. So that's no good. So instead, I have to use a wavefront sensor which indirectly measures the quantity I'm interested in. In this case, a Shack-Hartman sensor measures the first spatial derivative of the shape of the wavefront, of the aberration. Very, 30-second tutorial. I divide the pupil of my optical system into sub-apertures with a lenslet array. That is to say, a set of small, closely packed lenses which produce images on a detector of a source that's off there to the left, a collimated beam of an unresolved source, If the wavefront coming in is flat, I get a nice square grid of spots. If the wavefront is aberrated, then the spots all move, where each spot, let's look at this one here, this spot is deviated upwards because the little local piece of wavefront here tilted that away. So that spot moved up. Now, the spot locations, how they've shifted in this image compared to that one, gives me a measurement of d phi by dx and d phi by dy. Now all I have to do is a simple two-dimensional spatial integration, and I have my wavefront estimate. Here's an example of a real Shack-Hartman. This is again from one of my trips to that same EOS telescope on Haleakala in Maui, where we deployed a wavefront sensor. This one uses an InGaAs focal plane array, so it's sensitive to 1.6 microns. But this is some calibration data we took looking at a star, and you can see each one of these spots is an image of the star through a small piece of the pupil, and it's dancing around a little bit as the local atmospheric tilt above that piece of the telescope changes. And this movie is slowed down by at least an order of magnitude compared to real time, but you get the sense. This is what we're trying to measure. So this is a normal Shack-Hartman. Almost all adaptive optic systems in the world use a sensor that looks like this. We're proposing to go one step further and use a sensor that produces an output that looks like the image on the right. So here's the scene, the situation. We have a scene that we're interested in deblurring on the left. Here I imagine the scene sort of seen side on with three particular points in the scene called out, and they send cones of light through layers of atmospheric aberration to my lenslet array that's defined in the pupil of my optical system. And each one of these lenses forms an image of the entire scene, so we get a little grid that looks like that. What you can observe just from the geometry, and this is purely geometrical optics, there's no physical optics, there's no Fourier optics involved in this diagram here, it's all geometric, is let's look at this point here. There's a piece of wavefront at a particular range which is common to this point as imaged through that lens and this point as imaged through that lens. Right? So to the extent that there's a piece of aberration there, it will affect equally that point down in this image and that point in that image. And there are many, many more of those intersections, of course. Now, if you have a fully dense scene, you can define points, recognizable points, anywhere in the scene, and essentially trace rays to your heart's content through the turbulence to your lenslet array, and watch as, so what will the observable effect be? Again, if I put a piece of, if I have a tilt on this piece of wavefront here, it's going to move that red point as seen by this lenslet. It's going to move it laterally. It's going to contribute to the warping of the image. And the same component of the warping will be seen by that green point in that lens. So if I measure the differential warping at each point in each of these scenes, I will be able to recover line integrals of the wavefront tilt from each lenslet to each point in the scene. A line integral along this direction, a line integral along that direction, and so on. So there's information there about the three-dimensional distribution of the aberration. I have to extract it somehow, but at least you can begin to see that the information's there. Now we have to develop a clever algorithm to get it out. So again, at the block diagram level, this is the kind of system we're looking at. Light from the scene comes in. We have a beam splitter. It's always a critical component of any high-resolution imaging system that makes wavefront measurements. You have to steal a fraction of the light to feed your wavefront sensor, while the rest of it goes to the imaging camera, and that produces the image that eventually you're going to want to deblur. So we're beginning to do this in the lab. Here's an example of what one of these imaging Shack-Hartman sensor outputs looks like in the lab, where we're using an infinitely flexible scene generator called an iPad. Greatest invention ever. It does everything from taking pictures to producing the light for you, and by the way, it's a computer and will do the analysis as well. So it's the optical engineer's tool of choice. So anyway, what we did was we put an image of an Air Force resolution chart on our iPad, sent it through the system, and this is what you see on our wavefront sensor, which has a 6x6 grid lenslets across it. And we're in the process now. My student, one of my students, is busy analyzing the data from that system to try to estimate the aberration that we have put in here with a couple of engineered phase plates with atmospheric style aberration on them. But here's how the analysis in principle goes. So back to our movie of the ship in the Gulf of Mexico. If I break this image up into a bunch of little patches, then I can track how each patch moves around. If I look at the high spatial frequencies in the image here that represent this piece of railing, I can see this upright moving backwards and forwards, up and down, left and right. And let me run that again. You can track that with simple, well, let's try this. No, back up. Yeah, go away. Let's try that again. Okay. You can track the motion of each little piece of the scene with a simple order cross correlation, or you can use optical flow methods and produce a little quiver plot that shows how each patch of the scene is moving around. So to the extent that these vectors are all the same length, the same orientation, that just indicates a global motion of the whole thing. That's not particularly interesting. It's the differences in those vectors that tell you about the warping of the image and that tell you the information about the those line integrals of atmospheric aberration between the sensor and the various points in the scene. And this is not intrinsically, no, we didn't invent this technique. It's being used in solar adaptive optics by a German group. It's been used for a decade now, but not on anything like this scale. So this is fulfilling one of our criteria for a wavefront sensor. It's giving us three-dimensional, well, it's filling two. It's giving three-dimensional information, in principle, as we shall see. It's not, I don't require any active beacon. Right? I'm relying on the high spatial frequency content of the image to tell me how things are moving. Now, one perfectly valid criticism is that if there is no high spatial frequency content in the image, I can't tell how things are moving, and that's absolutely true. So there's a piece of image here where it's just a blank white wall. Right? My argument there is if there's no high spatial frequency content in the scene, there's nothing interesting for me to see, so I don't care. Right? Now, it's an ongoing area of research how a patch of image that has no high spatial frequency content will contaminate my estimates of the slopes and therefore screw up the entire thing. I don't know the answer to that yet. We're working on it. Okay, so I have now taken, so you can imagine that this image is what you would see through each one of my subaperture images here. So I get a warp map for each one of these guys. A warp map that looks like this, dynamical motion of those little vector plots. Now I have to do the tomography. I have to solve all of these line integrals from the sensor to the scene of atmospheric tilt, and I have to transform that into some understanding of the three-dimensional distribution of the aberration. So effectively, I've computed line integrals along my line of sight. I want to remap the integrands onto layers that are transverse to the line of sight. How do I do that? So here's how we set up the problem. So we postulate, and we'll get to how we do this in a second, some number of discrete layers of atmosphere, of aberration between the sensor and the scene, each of which is discretized into some number of phasals. There's a little element of phase. And we discretize it because I don't know how to do the continuous problem, and computers operate in discrete space, so it's a natural match there. So now I can write a couple of equations for my measured x gradients and y gradients. This essentially is the integral, right, in discrete space, and integral is a sum, of course, over each of the layers and over each of the phasals. So there's a little window function. All this does is it picks out which elements of phase in my three-dimensional distribution contribute to each measurement that I make with my sensor. Here's the real gradient that I want to estimate, and there's my favorite band again, right? The ubiquitous noise. So that's the problem that we have to solve. We can rewrite those sums in the following way. It's all just linear algebra, so I can rewrite the sum as a vector matrix multiplication. Here's the matrix. Here's my vector of measured x and y gradients for across each subaperture, across each point in the scene. I just lexicographically order them into an enormous column vector. It doesn't matter what the ordering is, as long as I remember what it is and keep it constant throughout the problem. Then I can postulate that there is a general linear mapper to take me from my measurements to those phases defined on each of the layers. And I'm sort of skipping it. I've talked about wavefront gradients at this point, but for going from gradients to integrated phases is merely another spatial integral. That's another linear operator, so I can simply roll that into my matrix there. So I can go directly from my measured gradients to the phases that I want. And I can rewrite that as a very simple linear equation. These are my measurements. Those are the things I want. How on earth do I calibrate that matrix? That's where the the black magic is. So once we have these phases, the three-dimensional distribution of the phases in our medium, then we can do something. We can use those to compute point spread functions and do something to correct the error. So here's our approach to building that tomographic reconstructor matrix R. It's called R because in adaptive optics and this sort of work, that operation is called wavefront reconstruction. So we use a set of basis functions. These are basis functions defined on the phase, the phase at each of the planes. We just use Fourier modes with added tip and tilt, because tip and tilt is not particularly well represented by Fourier modes, but it happens to be a very important error in the atmosphere. There's a power spectrum of aberration in the atmosphere, and tip and tilt is one of the major components that we have to worry about. Let's see how we do it for time. Better speed it up a little bit here. So in the computer, we measure the influence of each of these modes on our wavefront gradients. So here's a mode. We can plug in a mode here and measure gradients and build an influence matrix that tells us if there were a mode that looked like this at one of my layers, here's what my wavefront sensor would measure. And I can do that for all the layers, all the modes, and then my job is to invert that matrix, and I can do that with my favorite black magic tool called singular value decomposition, or a more Penrose pseudo-inverse. I can take noise into account if I want to. How do I define how many atmospheric layers I care about? This is one of the tricks that we use. So actually we use an autocorrelate. Let me just jump to this slide. This is real measurements from a conventional Shack-Hartman wavefront sensor, again at my favorite Air Force telescope on Haleakala. This is one of the gradients of, I forget whether it's the X gradient or the Y gradient, but it's one of them. And if you just sort of squint your eyes a little bit and introduce an artificial blur function, you can see a general motion of phase errors from the bottom right to the top left. That's wind advecting frozen phase over the top of the telescope. Now if you take a three-dimensional spatiotemporal autocorrelation of these data, this is what you get. You find lines of high correlation that correspond to important wind-driven layers of aberration, and the direction and speed of each of these little zooming blobs is the wind vector. So you know how many layers there are from how many little funky blobs there are, and you know what their wind vectors are. And we do this in our numerical restoration code. So that tells us how many layers there are and how they're moving. We need also to know the layer ranges. So what we've done to compute how many layers there are is autocorrelate essentially a single subaperture's, the whole pupil's, I should get this right, we autocorrelate the whole pupil's measurements of gradients along a single line of sight. If we instead cross-correlate single subapertures across the field, then we get the angular speed, and by looking at the angular speeds and the beam crossing times of each of these layers, we get the ranges, essentially by triangulation. So by using these cross-correlation autocorrelations of the gradients, we can define the atmosphere. We let the data tell us what the atmosphere is doing. And then we can build our reconstructor matrix on the fly and recover what the phases are in 3 dimensions. Once we've done that, then we can calculate the point spread function at every point in the field by projecting rays from each point along that line of sight to our pupil. One other thing that we do that I'll touch on very quickly, we use a frozen flow approximation. As I said, we've measured how many layers there are. We've also measured their wind vectors. And that allows us to do a little bit of dithering, as it were, interpolation. So natively, we can only sample spatial frequencies of the aberration that are commensurate with the size of our subapertures. They act as sort of low-pass filters, if you will. But if you have a wavefront that is being micro-stepped across the top of your subapertures, you can interpolate higher spatial frequencies of the wavefront error. And that's what we've done here. Imagine we have a piece of aberration that looks like this. Here's our pupil, and here are our sampling points. Then this is the sort of thing you would natively expect to get. This is, by the way, an actual reconstruction of real data from, again, that same telescope. This is at the native 32 by 32 grid of that wavefront sensor. But if you do the micro-stepping thing, you let the wind advect the phase over the top of the pupil in this direction. And here, we're in the frame of reference of the phase, so it looks like the pupil is stepping across the aberration. And you can see that our density of sampling points effectively goes up. And we can reconstruct something that looks like this. So we can infer higher spatial frequencies of the wavefront error than are natively sampled by the sensor. So that lets us do a better job. All right, so we haven't done this for real yet. We have done it in a fairly sophisticated simulation. So I'll run this movie in just a second. Here's a pristine image ripped off of Google Maps of my favorite College of Optical Sciences, seen from space. Here's what it would look like at the diffraction limit of a 50 centimeter aperture, 700 nanometer wavelength, looking down from 10 kilometer altitude. So if I put in a 4-layer atmosphere, this is what it would look like before and after correction using all of this machinery. And is that going to run? Or no, it did earlier. Well, I don't know. It's supposed to run. Maybe not. Well, that's sad. I guess it's not going to let me show my movie. Yeah. Anyway, well, take it from me, it's a movie, and all of the frames of the movie look sort of like this. And after we've done our magic tricks, it looks like this. Here are the point spread functions on axis, well, in the center of the scene, before and after, blown up by a factor of 8. By the way, here's the isoplanatic patch size. This is the size over which a PSF is shifted variant. So it's tiny compared to the scene. It's about 30 times bigger. So we are indeed correcting wide field of view compared to the isoplanatic patch size. Quantifying that performance improvement, here are the MTFs. Here, the blue line, here's the long exposure. The blue line here is the long exposure MTF without correction. The green line is when we do the correction, and this is the diffraction limit for a circular aperture. This quantifies the transmission of spatial frequencies of the wavefront error. We're not, the green line is how good we do. We are not at the diffraction limit, although we do go all the way out there. The image correction is not that good, but it's far, far better than before we do the correction. So, to summarize, here's our algorithm. We start out with wavefront sensor images, calculate the warp map for each one. That lets us then get the number of atmospheric layers and their ranges from all of these correlations. We apply tomosynthesis to map the wavefront slopes onto atmospheric layers. Compute the frozen flow models to get the high spatial frequencies. Turn those into wavefront phases and then point spread functions over each point in the field of view. Take them out with a Wiener filter from the full field images, and there's our high resolution result. So I will leave it there since we're running very short of seconds. So it looks like tomographic wavefront sensing from a wide scene is a promising thing. And I hope next time I'm back here, which I trust will be in a little less than another 30 years, to show you real results from the bench and hopefully a fielded system as well. Thank you very much.
first general, then technical. So what sort of time frame do you expect? Also, if I understand it, you record your wavefront sensing images and your real images at the same time, right?
That's right.
Then you have to post-process the wavefront sensing and then apply it to your real images. So on sort of what kind of timescales do you expect this working? You know,
about 3
realistically,
milliseconds.
ideally.
About 3 milliseconds for the whole thing per frame. So I think we can generate about 300 frames per second from a system that's about the scale I talked about, 50 centimeter aperture, 5 by 5 or 6 by 6 array, and the field of view of a tenth a degree or so.
And, the cross correlations that you were mentioning to get your map of distortions and whatnot.
Yeah, right.
So how many images do you need? How many cross correlations do you do to kind of build up a mean kind of flow?
Right. So at the moment, what we're using is a leaky integrator on the images themselves to give us a template for cross correlation. And I don't think that's the smartest thing to do. I think there are better ways to do it. So if anybody has better ideas, I'd be delighted to talk to you probably tomorrow at this point. But we end up doing about something like 3,000 cross correlations per cycle. We do it hierarchically, starting with full frame and then going down to smaller and smaller patches. So we do a lot of cross correlations, but they're very small, like 8 by 8 pixels.
More questions?
I have a second question. Oh, you? I'm sorry.
Go ahead.
Oh, yeah. About the frozen flow thing, so that's something people have done before, I guess?
No, well, we weren't aware of anybody else having done it before.
Oh, okay,
Yeah.
cool. Over what kind of angles compared to the isolytic patch do you think, and what kind of time scales do you think it's frozen over? Because surely it changes over some time scale.
It does. There's boiling of the turbulence as well. So there have been measurements made, and it changes. About 50% of the correlation has gone. The peak has decayed by 50% after about 100 milliseconds. So that's quite long compared to the time scales we're concerned about. So we can take advantage of it. We haven't found a limit yet to the field of view, and that's because we haven't pushed far enough yet. But we're pretty confident that over the kinds of fields of view we're talking about, like 10th of degree, and these ranges, we can trust it. So that's, yeah, good question.
I have a question. So when you build this reconstruction matrix, you select the wavefront modes.
Yes.
How do you determine that?
How do we determine what the modes were?
Yes.
I like these modes. No, I don't mean to be flippant, but yes, that's pretty much what it is. So we actually did this experiment with a square aperture, and the Fourier modes are a nice choice for that because they're easy to compute and they're orthonormal. If we're using a circular aperture, I have another favorite set of modes called disharmonics, right, which are essentially the Fourier equivalent over a circle. They're the solution to the Laplacian over a circular aperture rather than a rectangular aperture. And they're also orthonormal and easy to implement on a deformable mirror. So
Okay.
I would use those.
Thanks. There's no further questions. We're going to have a coffee time.
Oh, that's right. I can save the coffee
After
now
this,
that my flight got canceled.
After the talk, and you can ask more questions.
Yay.
Okay, let's thank our speaker one more time.